Welcome to Chemistry Travels, and we are moving on to the fourth part of chemical kinetics. So in the first introductory part, I did talk about the various factors that affect the rate of a reaction. Those were the concentration of the reactants, then we had pressure in case of gases, followed by temperature, and finally catalysts that affect the rate of a reaction. And it was the concentration of reactants that we were dealing with in particular in the previous videos. And now we are moving on to the other three, that is pressure, temperature and catalyst. Let's see how these three factors alter the rate of a reaction. First, we'll look into the pressure, the effect of pressure on the rate of a reaction. So before we move on to understand the effect of pressure, we should understand how chemical reactions occur. That is, if I have some reactants getting converted to a product, they occur by the collision of the reactant molecules. The reactant molecules should collide with each other effectively, and those molecules having suitable energy would collide with each other, and those molecules in proper orientation with those suitable energies would get converted to products after collision. Okay. So if I consider gases, what happens is when I apply pressure to the system, the reactant molecules are now getting compressed. That is, they are coming closer to each other. Their volume is decreasing, and the initially gas molecules that were initially spread out has now come to a more closed space. So they are compressed, and in a compressed state or in a closer space, it is more probable that the number of collisions would be greater. There is a probability of having greater collisions within a closed space, thereby leading to a greater product formation or a faster product formation, I can say. And hence I can say that when I increase the pressure, the volume of the system would decrease, the gas molecules come closer to each other. Now the number of effective collisions increases, thereby rate of the reaction also increases. And this is not applicable in case of solids or liquids, where pressure does not considerably change their volume, like they cannot be compressed by applying pressure. Okay. Now if I consider a reaction A, where reactant A is getting converted to products B and C, all this A, B, C, everything being in gas state, and I can actually write an integrated rate law for first order for this particular equation for first order reaction. Consider this to be a first order reaction, and let us write an integral rate expression for this particular reaction. So I can say that now at time t equal to 0, that initially the pressure of my reactant A was some Pi. I represent the initial pressure of A to be Pi, and B and C having pressure 0 because they are not formed at the initial point, right? Now the time t, at some time t, after a time t, the reactant's pressure has reduced to Pi minus x, while the pressure of B and C, the products pressure, turns out to be x. Okay, B has a pressure x, C has a pressure x, whereas the pressure of A has reduced from the initial pressure Pi to some value Pi minus x. Now at time t, I can say the total pressure of the system. Now the system has some amount of reactant and some amount of products B and C. So the total pressure turns out to be a sum of the pressure of all these. So it is Pi minus x plus pressure of x, B plus the pressure of C, that is Pi minus x plus x plus x. Now this minus x and plus x, I can cancel them off, and so the total pressure of the system can turn out to be Pi plus x. Okay, from this particular equation I can write x to be Pt minus Pi. Okay, let that be there, and we can represent this equation x, the value of x to be 1. Okay, equation 1. Now let's consider the final pressure, that is the final pressure of A was Pi minus x. That was the final pressure at time t. Now instead of this x, I am substituting the value of x from equation 1, so that the final pressure of A turns out to be 2 Pi minus Pt after substituting the value of x from equation 1 that we already derived. Okay. Now we know that for first order reactions, the integrated rate law in terms of concentration was K equal to 2.303 by T log initial concentration by final concentration. Now that we are considering the pressure factor, we need to replace these concentration terms with pressure terms. So the integrated rate law for first order in terms of pressure can be K equal to 2.303 by T log P initial pressure by final pressure. And initial pressure was represented as Pi, for A. For the reactant A, the initial pressure was Pi. So, Pi by the final pressure, we found it out to be 2 Pi minus Pt. So, substitute that here 2 Pi minus Pt as the final pressure, and we can say that K equal to 2.303 by T log Pi by 2 Pi minus Pt. Okay, and this equation is the integrated rate law for first order in terms of pressure, that is for gases. Clear? Let's move on to the next factor, that is the role of temperature on reaction rates. So, as I already told, chemical reactions take place when reactant molecules collide with each other to form the products. And these reactant molecules should have sufficient energies and they should be in suitable orientation so that they can have effective collisions and finally form the proper products, right? So, if I say I have reactants A and reactants B that are colliding with each other to form products AB, on their pathways, they form an unstable intermediate which is termed as the activated complex. So, this complex being unstable, it stays for a very short period of time and then it immediately decomposes and finally forms the products. Okay. So, this can be graphically represented in this form where we have a graph between potential energy and reaction coordinates. So, reactant slowly gets converted to an activated complex, the energy increases the activated complex and then it finally forms the product P. So, this energy gap that we have between the reactants and the activated complex is called as the activation energy, termed as EA. Okay, this is the activation energy, and only those reactant molecules that have energy greater than this activation energy, they alone can cross this energy barrier, this activation energy barrier can be crossed by only those molecules whose threshold energy is greater than this activation energy. Those can cross this barrier, form the activated complex and finally form the products. But there will be certain molecules in my reactant species whose threshold energy cannot cross this energy barrier, thereby they cannot cross this activation energy and they cannot form the products. Okay. Now, how this concept can be used in understanding the effect of temperature on reaction rates. And it was Arrhenius who proposed the effect of temperature on reaction rate, where he told that for every 10-degree rise in the temperature, the reaction rate or rate constant for the reaction, that is K, it nearly doubles. That is, if I have a temperature T and the rate constant to be some value K for a particular reaction, when the temperature increases by a factor of 10, that is temperature becomes T plus 10, the rate constant nearly doubles, that is it becomes 2K. Now, to prove this, he used the Maxwell Boltzmann distribution curve, and using this he was able to explain this particular effect of temperature. Okay. Now, what is Maxwell Boltzmann distribution curve? It's a graph that you see here between kinetic energy and the fraction of molecules. So, when you say fraction of molecules, it is the number of molecules at a particular energy E divided by the total number of molecules. So, and the graph that we have, the Maxwell Boltzmann distribution curve, just consider the green graph alone for the time being. Let's just consider the green graph. It's like a mountain shaped graph, right? Something that goes up and then it comes down. Okay. This is the Maxwell Boltzmann distribution curve, and it simply means to say that when you have some reactant molecules, not all the molecules will have same kinetic energy. A set of molecules would have some particular kinetic energy E1, another fraction of molecules would have some kinetic energy E2 and so on. So, if I consider just the green for now, what I can see, with the increase in kinetic energy, the fraction of molecules having those kinetic energies also increases. Then it reaches the maximum point, top point or the peak, and then from there it further decreases. That is, at this peak point, the fraction of molecules having that particular kinetic energy would be the most. Most number of molecules in my system would have that particular kinetic energy. And then further increase in the kinetic energy would cause a decrease. There will be lesser fraction of molecules having higher kinetic energies. Okay, this is the graph. Now, if I consider this Arrhenius case of two temperatures T and T plus 10. So, the green graph would correspond to T, temperature T, and the red graph is the distribution curve for temperature T plus 10. So with increase in temperature, what we see that is the Maxwell Boltzmann distribution curve shift towards the right, or I can say that this most probable kinetic energy that we have at the top, at the peak, that shift towards the right. That is, now most fraction of molecules in my system would have a higher kinetic energy at a higher temperature. At T plus 10, this most molecules are having a higher kinetic energy compared to the kinetic energy of most fraction of molecules at temperature T. That is what you understand from the shift. So now how can you relate this in this? So since most of my molecules now, look at their kinetic energy, now most of the molecules at higher temperature, they are having a higher kinetic energy. So which means that now most of my molecules have the ability to cross this barrier, or their threshold energy is greater than the activation energy, and they can now actually form the activated complex and form the products. Compared to the previous case where only their kinetic energy of most of the molecules were low, so they had a lower energy and most of the molecules were not able to cross, but at higher temperature now kinetic energy increased, so they have the ability to cross this barrier and form the products. So reaction rate also increases. Okay. And if you also look into the graph, suppose let's say that at this particular energy point I have my activation energy for a particular reaction. This is my activation energy. Now when you look at the area under the graph, you can see that the area under the graph is the fraction of molecules that are reacting at that particular temperature. Now if this is the activation energy, so area under the graph is all those molecules having energies higher than the activation energy. So those are the molecules, this area under the graph will be the fraction of molecules that react to form my product P. Now if I consider the red one, it is higher temperature and their area under the graph is more, and this green one is the molecule. So the red one is more, the area under the graph is more, which means that more molecules have energy greater than the activation energy, more molecules will react. But at lower temperature T, the area under the graph is less, it is only the green shaded portion, so it is lower. So lesser number of molecules would react, so their rate or rate constant would be less. And using this, he has proved his concept of doubling of rate constant with every 10-degree rise in temperature. Clear? And Arrhenius has also formulated an Arrhenius equation that relates the rate constant and temperature, that is K equal to A into e power minus EA by RT, where K is my rate constant. Then we have A, which is the Arrhenius constant, or it's also termed as the pre-exponential factor. Yes, it does come before the exponential factor. Then we have the activation energy EA, which is in joule per mole, and we have R, which is the gas constant, and since activation energy is in joule, my gas constant also should have the unit in joules. So the value is 8.314 joule mole inverse Kelvin inverse for R. And finally T is the temperature, and since gas constant has Kelvin in its unit, temperature should also be in Kelvin. Okay. And if you look at this equation itself, you will understand that when you increase the temperature, if T value is increased, this power value EA by RT will definitely decrease, and hence this overall the K value will increase. That's understood from this equation. Now we can also take the log of this, the natural log. I am taking the natural log of this equation. So ln K becomes equal to minus EA by RT plus ln A, because log of e power something will be actually that power value. Log of e power x is x, log of e power y is y. So whatever is the power, that will be the log of e power something. So this becomes ln K equal to minus EA by RT plus ln A. Okay. Now this equation has the form y equal to mx plus c, which is the equation for a straight line. So I can plot this equation as a straight line for a graph between ln k being y and 1 by t being the x. So when I have 1 by t versus ln k graph, it will be straight line that is actually declining, because my slope of this graph from the equation, it is minus EA by R, and the intercept of this graph is ln A. Okay. Now let's consider a chemical reaction. A particular reaction is carried out at two different temperatures, T1 and T2. So definitely at T1 they will have some rate constant K1, and at T2 they will have a rate constant K2. But since it's the same reaction, their pre-exponential factor A remains the same and their activation energy also remains same for the same reaction. It's just that we're changing the temperature and thereby the rate constant changes. So we got two different equations, 1 and 2. Now if we subtract 2 and 1, like 2 minus 1, what we get, ln of K2 minus K1 becomes equal to EA by RT1 minus EA by RT2. Okay. Now ln x minus ln y was seen as ln x by y. We already saw all that in our initial videos. So ln K2 minus ln K1 can be written as ln K2 by K1. That is equal to, now on both these terms I have EA by R common, so I take that out. So it is equal to EA by R into and 1 by T1 minus 1 by T2. So ln K2 by K1 equal to EA by R times 1 by T1 minus 1 by T2. Or instead of this ln, I can also have it a common log, which is log, log. So we saw that ln is 2.303 log, and that 2.303 value I am just taking it down, so that final equation comes out to be log K2 by K1 is EA by 2.303 R times 1 by T1 minus 1 by T2. Okay. So this is the Arrhenius equation that we can have when we have two different reaction temperatures. We can have this equation for as the Arrhenius equation. So that's it for today's video, and I hope you understood whatever has been discussed today. Thank you so much.